In this quick tutorial, I'll show you how to calculate the acceleration of the center of mass. Notice that we have 3 points, one here, one position here, and one position here, and they have a force vector extending in these directions. To calculate the acceleration of the center of mass, we use this formula shown underneath, where the acceleration is a vector and it is equal to 1 over the total mass of all particles times the sum of all forces, their x and y components. So the very first thing that I want to do to simplify things is to multiply both sides by m for this equation. And if I multiply both sides by m, I end up with m, which represents the total mass, times the acceleration. And since acceleration is a vector, I will write down a with a arrow symbol at the top, and cm represents center of mass. And that's equal to the sum of all force components. At this point, I can easily add up 18, 12, and 20 together. So 20, 12, and 18 make 50. And I will replace this m with 50, and this will serve as a scalar quantity being multiplied to the vector a. So I'll just write down vector a for now. And I will look at each of these points and break them down into their x and y components. So for that, you'll need to use some trigonometric functions. For instance, this one is going to the top right at an angle of 45 degrees. That can be broken down into two separate vectors. So a y component and the x component. To find the x component, we will take, remember the trigonometric function, cosine relates the adjacent side times the hypotenuse, which is 30 newtons. So cosine theta is equal to the adjacent over the hypotenuse. The angle is 45 degrees, and adjacent is what we're looking for, and the hypotenuse is 30. So solving for x, I have 30 cosine 45 degrees. Multiplying these out will give me the magnitude of that arrow. So I will write that in. I have 30 cosine at 45 degrees. And since I'm breaking the vector into its components, I need to multiply all x components by the unit vector I, and all the y components by the unit vector j. So to represent this one, rather than using cosine, I'll use sine. So sine 45 is equal to the opposite, which I'll represent as y, over 30. Solving for y, I have 30 sine 45 degrees. So I'll take this expression and write down plus 30 sine 45 degrees times the unit vector j. Now, one thing to keep in mind before we continue on with the other two forces is that because this one was in quadrant 1, you know that both of these statements should be positive. But if this was happening somewhere else along the xy plane, for example, it was happening in the second quadrant, then you would have to recall cast, which says that only sine is positive in the second quadrant and everything else would be negative. So just keep that in mind if your question is a little bit different than mine. So to analyze this one next, notice that this vector is only going down. There's no x component. So the way we would handle it is we would say plus, we would write down 40, and notice that it's only a y component. The angle is 270, right? So it's going downwards, so it's 270 degrees. And because it's a y component, we write down sine 270 degrees. Multiplying this out, let me show you. 40 times sine at 270 makes negative 40. Now you could do it technically like this and write down sine 270 times 40, and you get negative 40. Or you can simply take 40 and put a minus in front, given that it's going directly down. That's okay as well. And don't forget that this is being multiplied to the unit vector j. Now this last vector here does not have a y component, only has an x component. So using the same strategy, I'll take the 24 newtons, multiply it to cosine, and the angle this time is 180. And because it's the x component, it's cosine 180 multiplied to the unit vector I. Let's find out what that is. 24 times cosine 180 makes negative 24. So you could have simply wrote down negative 24 instead if you wanted to, just by analyzing the vector given that it's going to the left. And now what we have to do is combine all the I components together and all the j components together. Let's use our calculator. So I have, for the I components, 30 times cosine at 45. That's equal to 21.21 plus this one, negative 24. And we get negative 2.78, or negative 2.8. Negative 2.8 I. For the j's, we will take 30 times sine 45 plus negative 40. And we end up with negative 18.8. Negative 18.8. And that's equal to 50a. Of course, at this point, you can divide both sides by 50. Now that I think about it, it's probably best had I not multiplied both sides by m at the very beginning. So dividing these out, negative 2.8 divided by 50 makes that value. And dividing these out makes negative 0.37. The units for acceleration are meters per second squared. And there you have it. That is how to calculate the acceleration of the center of mass.